Hello everyone, let's continue. So in the last video we introduced a term V of X which actually indicates the voltage at each and every point on this particular X axis. Okay, so for example this was V of 0 which is 0 volts, and this was V of X or V of L which is VDS volts. Okay, accordingly the effective voltage of this channel that will vary. And why is that so? Because you have this VGS which is applied at this point, which is applied at the gate. So your effective voltage will be VGS minus V of X. So for example, let's take an example. So at this point of time, your at this point of your channel, your VGS is 1 volts. Okay, your Vx is 0 volts. So your effective channel voltage, which is VGS minus V of X, will be 1 minus 0, which is 1 volts. Okay, similarly let's look into this point. Okay, over here V of X is VDS, which is 0.05 volts or 50 millivolts. Okay, the VGS is 1 volts, so your effective channel voltage at this point will be 1 minus 0.05, which is 0.95 volts. Okay, and the voltage across this channel will be lying somewhere between 1 volts to 0.95 volts. So that's why I said a voltage gradient over here. It goes from higher voltage to lower voltage. So channel voltage, it's not constant, it's gradient. That's the gradient over here because of the presence of VDS. If this was grounded, this was all constant. Okay, so now we have to identify what is the amount of induced charges in this particular channel in the presence of VDS. Okay, and here you go. So now now the charge which is induced in the channel, that will be proportional to the VGS minus Vx volts, which is the effective voltage at each and every point over here, minus threshold voltage, because threshold voltage is the one that is that basically turns on the transistors. So you have the induced charge is proportional to VGS minus Vx, okay, which is the effective voltage at each and every point, minus Vt. So when you try to expand it, it comes to the induced charge at each and every point is COX into basically Q equal to CV. It's a charge conservation principle. So Q equal to CV. So COX is this capacitance, which is gate oxide capacitance. It's epsilon ox by Tox, and I'll come to that formula. So you have the induced charge at each and every point of your channel is equal to COX into VGS minus Vx minus Vt. Okay, so with this formula, with this thing now in our hand, let's try to derive certain equations, because now we have the charge. So it's very easy to derive the current equations, because current is basically a function of your charges present in the channel. Okay, so we'll do a first order analysis over here. We have the charge present at each and every the induced charge at each and every point, proportional to or equal to COX into VGS minus Vx minus Vt, and COX is epsilon ox by Tox, and these are all constant. So for certain technology, for example, let's say 100 nanometer technology, Tox will be constant, that will be coming from foundry, and these are all the terms that we'll be using for the spice simulations. So before entering into spice simulations, we are building the background for it. So spice is a tool where we have to implement all our knowledge, all our understanding over here. So whatever we have understood from this point, let's say V of X, which was VGS minus Vx, and all those things, these all things has to be confirmed using spice, and we are building the basic. These are all the basic building blocks of understanding spice. Okay, so COX is epsilon ox by Tox, and Tox is again the one that is being given as a standard, as a constant. So epsilon ox is 3.97 into epsilon 0 relative permittivity, so it comes out to this particular value. And Tox is the oxide thickness. By oxide thickness we mean this particular oxide. It's a gate oxide. It's present between the gate and the p type substrate. Okay, so that's the oxide thickness, and that's constant, that comes from the technology node. Okay, moving on, we need to now from a device physics point of view, if you try to identify the currents, there are two kinds of currents that we see in the device physics point of view. So one kind of current is the drift current. So drift current is basically the current due to potential difference. So for example, you have two different points. Let's say you have one point over here, you have another point over here. If there is a potential difference between these two, there is a current flow, and that's called as drift current. Okay, that's drift current. And second, there is a diffusion current, that is because of the variation of the charge carrier. So for example, you have let's say a tank over here which is filled up with water. You have another tank over here which is empty. So now this tank has got more water than this tank, so water flows in this direction. And why that water flows? It's because difference in the water levels. and that's exactly diffusion current. Diffusion current is because is the current due to the difference in the carrier concentration. You can take this analogy. Let's say this is a tank which has got more carrier concentration. This is a tank which is empty, so there will be a current flow. But the scenario that we are talking about in this particular video, that's about drift current, because you have this particular thing at zero potential, you have this point at VDS potential, so there is a potential difference, and as a result of that you will see some small amount of current which is flowing from source to drain, and that's drift current we are talking about. We'll come to diffusion current because there are other so whenever there is a PN junction diode, and when these two junctions when the P type material comes in contact with the n-type material, there is a small amount of current because of difference in the charge carrier concentration. That's diffusion current. So we'll talk about that in a bit detail in the device physics slides. For now, we'll mention about the drift current, which is the current at this which is the current due to the difference in the potentials at this point and this point. Okay, so now we are aware that the drift current is what we saw now. So we have to now basically derive some equations for the drift current and see what all things are needed to identify the drift current. So now we know that there is a drift current which is flowing over here. The next job is to derive the drift current equation, which is a function of again of your drain to source voltage and VGS, and then use those equations to do the further analysis. Let's come to that point in some time from now. Okay, so the drift current is been measured as a velocity of the charge carriers multiplied by your available charges, and these happens over certain area, and that area is over the channel width. So now what is channel width? It's not visible from this particular structure of the MOSFET. We have to actually look the MOSFET from the top level. Basically we have to look into a cross-sectional view of this MOSFET from the top level. It will look something like this. So you have your channel, you have your gate, which looks from the top something like this. You have your source, you have your this source area, which from the top looks something like this. Okay, and you have your drain area, which from the top looks something like this, and your channel width is this one. It's an gate overlap area over the source and the drain. So current is a function of channel. Current is basically a measurement of the velocity of the charge carriers multiplied by available charge over this complete channel width. Because from here you are able to see only the channel length. But if you move into the top view of this particular MOSFET, you'll be able to see the channel width. So the current is basically measure of the carriers, measure of the velocity of the carriers over this complete area. Okay, so things have become analytically theoretically pretty much clear over here. Now we need to just we have to just put some values over here. We have to put the value of velocity, we have to put the value of available charge, and integrate it over the complete channel width, and that's where you will get your current equation for source to drain for this kind of scenario. And the scenario is where your VGS is 1 volts, it's greater than VT, your VDS is very small, which is 0.05, and you have your threshold voltage as 0.45. Okay, so given these values, given the drain current is a function of velocity of charge carriers and the available charge over channel width, we have to just plug in those values and integrate it completely over the channel width. So let's try to we need some more time over here, so let's try to do all this in the next video. Thank you.